this time we're gonna start with bounds on codes, and today we're gonna see the Singleton bound, which you might already know. So we assume we have a NKD code over FQ, and the Singleton bound says the following. It says that D is at most n minus k plus 1. Okay, so I'm not going to prove it in all detail because we will see this later on as a corollary to the Griesmer bound, but I'll give you a sketch. So one can show that actually D is the minimum of, let's say, D prime in the integers, such that there are D prime linearly dependent columns of H, where H is a parity check matrix for C. And now we also see immediately that D is also the maximum of, say, well, let's say D twiddle, such that all D twiddle linearly independent, all D twiddle columns of H are linearly independent, and then of course plus 1, because we want the minimum of the ones such that there exist linearly dependent columns of the parity check matrix. And now if we assume that we know this equation or this equation, which is the same, then, which you can prove by linear algebra, so I'm not gonna do it, but you can find a proof in various lecture notes about coding theory, and I think I'll also give a reference in the video description, so you'll find why this is true. But assuming that this is true, we know that D is at most n minus k plus 1. Why? Because we want, if we take this here, all columns of H are linearly independent. An upper bound for this maximum is clearly the rank of the parity check matrix, and the rank is equal to n minus k. So the rank gives the dimension of the image of H, and so this means that there are n minus k linearly independent columns in H and not more. But it doesn't say that all columns of all n minus k columns are linearly independent, so it's at most n minus k. And now we are done because we have this, and that's what we wanted to show. All right, so let's go on with a definition. So a code is called maximum distance separable code. And again, we assume, let's maybe say a linear code. We always assume we have linear code. And again, let's say it's an NKD code. And for short, we call it MDS for maximum distance separable, so MDS code. If D is equal to n minus k plus 1. So that means that this upper bound is that it exactly has minimum distance of this upper bound. Okay, great. And I'm not sure yet, maybe later we will see some examples of some MDS codes. There are, for instance, Reed-Solomon codes, or also, which you might have heard, or generalized Reed-Solomon codes. And maybe we'll see something about them, maybe not, I'm not sure yet. But what we definitely will see is the Griesmer bound. So let me just write it down. So we're gonna start with the proof next time. But let me write it. So here we have the Griesmer bound. Again, we have a linear NKD code. And we assume that the dimension is not 0. And then we have n is at least some a equal from 0 to k minus 1. And then d divided by q to the I. And then we round it. And now just a short remark. The Griesmer bound implies the Singleton bound. Why is that the case? So we have n greater than, now let's take the I equal to 0 term, then we have d divided by 1, so, and well, but that's just d, plus something else. Let's maybe write it down completely. So d divided by q to the I. So well, this is d, and this sum here is d is clearly non-zero, so we know that for every term we get at least a 1, so this is at least k minus 1, and now if we write it in another way, we get that d is at most n minus k minus 1, which is n minus k plus 1. Alright, so far so good, and yeah, next time we will start with the proof of the Griesmer bound, and see you then, and bye.